Our next talk is the winner of the Best Paper Prize in the Novel Applications track. It's Planning for Social Interaction in a Robot Bartender Domain, and the talk will be given by Ron Petrick. This is joint work between Ron Petrick and Mary Foster.
Thanks, Maria. So on behalf of Mary, we'd like to thank the organizers of the special track and the selectors, the program committee, for selecting our paper as best paper. We think it's a really fun domain. I'm going to talk a bit about the domain and how planning comes into this space. So, why is this not advancing?
Just switch on.
Oh. There we go. Okay, so I'm going to start out with what looks like the beginning of a really bad joke. Two people walk into a bar. And so we have a scenario here. Two people walk into a bar, A and B, and they approach the bartender. And the bartender says to the first person, "How can I help you?" And the person says, "Well, I'd like a pint of cider, please." And then a third person, person C, comes in and tries to attract the attention of the bartender by gesturing, maybe wildly waving his hands across the head. And the bartender says to this new person that came in, "Well, how can I help you?" And then the person says very calmly, "Well, I'd like a pint of bitter." And so the bartender proceeds to serve the third person that came in, then addresses the second person, part of the original group, says, "Well, what would you like to have? A glass of red wine?" The bartender serves the second person, and then finally serves the first person that ordered way back at the beginning of the interaction. Well, sorry, seem to be having... I'm pretty sure I didn't... Okay. Seems to be a little flaky for some reason. So then we have a second scenario. Two people walk into another bar. And in this case, the two people walk up to the bartender. The bartender says, "Well, how can I help you?" The first person says, again, "I'd like a pint of cider." And now this third person walks up and tries to attract attention of the bartender. In this case, the bartender, first of all, nods at the first person who ordered the drink and then says to this new person, "Just a moment, please." Serves the first drink, addresses the second person, "What would you like to have?" A glass of red wine. Serves the second person, and then thanks the third person for waiting, asks them what they'd like. Person orders their drink, and they get their drink. What's interesting if we look at these two interactions together is that from a purely task point of view, both interactions actually achieve the task goals of everybody involved. Everybody gets a drink in the end. However, if we look at the second interaction, we can argue that the second interaction is actually much more socially appropriate than the first interaction. There's certain expectations that we have of behavior, especially in service scenarios, and these are played out in the second interaction, but not necessarily so much in the first interaction. Now, I put a star beside socially appropriate because socially appropriate depends on a whole lot of things. It depends on cultural things. It depends on your local pub and what's considered acceptable behavior there. But at least I'm arguing here in this case that in the second scenario, we have a scenario that's slightly more socially appropriate than the first. Well, in our case, the trick is we want to deal with this as our bartender, this friendly robot here with this giant industrial arms and this robot cat head. This is our bartender, and we want to look at this problem of social interaction and socially appropriate interaction in this setting. So the motivation behind this problem is really coming from the social robotics type of community, where successful task interaction often relies on appropriate social interaction, which is inherently multimodal. I mean, it involves things like speech, it involves gesture, it involves gaze. There's a whole lot going on here in this problem. And the robot needs to be able to respond to the customer's request in a dynamic setting. We've got people coming and going, people wanting attention, people that don't want attention. And usually the interactions are quite short. You have a couple seconds to find out what the people want and to get the interaction right. And if you don't get it right, then you've probably failed. What's interesting about the interactions is that they incorporate a mix of different types of actions. So there's both task-based aspects, so these are things like actually ordering, handing over drinks, and social aspects, so managing the multiple interactions, who's next, nodding at people, all these things that are part of the social management of the interaction. And the particular domain that we're looking at here is a case where we have multiple human customers. They're trying to order drinks in the presence of other people which might just be hanging around. They're not actually necessarily seeking attention. Now, when you start looking at this problem more closely, you see that a key modality in human social interaction is natural language, and natural language dialogue in particular. And there's a lot of parallels to planning in dialogue. And so, with dialogue, a speaker's really trying to change the mental state of the hearer, in this case by applying actions to correspond to the utterance of words or sentences. And this is a link that hasn't been lost on the natural language community. And if you start looking back at the literature, this actually has quite a long tradition, especially going back to work in the 80s. Recent work, though, coming out of the natural language community has tended to actually separate the task aspects of the problem from the more natural language aspects of the problem, where they tend to use more specialized approaches. So we see things like finite state machines and information state processing, various rule-based approaches. And so the challenge with this work for us was really to see, could we replace the behavior of the traditional interaction or dialogue manager using more general purpose planning techniques that are familiar in this community. Now, we are working in the context of what is a multidisciplinary architecture on the system. So in terms of, it's actually, it may not look it here, but it's a pretty standard three-level architecture. In terms of input modalities, we have things like a vision system and speech recognition, which are providing inputs into the system. A state manager, which is trying to make sense of all that. The planner right at the top, making high-level decisions about what the robot should do next. And then an output planner, which is taking the high-level outputs that the planning system will make and turning them into the various modalities we're working with. So these are things like what should we say to the customer? Should we gesture a certain way? Should a cat smile at the user or not? And of course, the real world is involved in this process. If you're interested, there's a lot of details in the paper, and we had a short paper in the application showcase, and so I recommend that to you. If we drill down a little bit at the actual problem, from the planning point of view, what we have is really inputs coming from some social state recognizer, which is processing vision and speech in the world, turning them to a form that we can work with, and then the output from the planner, the plans that we produce are going to this output mechanism which turns what we've decided to do in terms of speech, possibly moving the arms, nodding the head. Now, the domain, as I said earlier, includes quite a mix of actions. So we have physical actions, things like handing over drinks to a user. We also have sensing actions, things like asking the customer for information. What drink would you like? And in many cases, our sensing actions really map onto the different dialogue acts, especially the information gathering dialogue acts that we have in this space. And then there are other actions that I wasn't really sure, what category they fall in, but they're really for handling the social behavior. And so these are things like acknowledging that we got a drink action, maybe thanking a customer, saying goodbye to them at the end of the scene. These are things that are needed for the interaction, but they don't necessarily fall into these other categories. So if we look back at the interaction that I had, the second interaction, you can see things like serving here as an example of maybe a physical action, things like asking, how can I help you, what will you have to drink, or examples of sensing actions. And then there are various aspects in the interaction, saying just a moment please, thanks for waiting, and things like nodding. So humans pick up on things like if I say something to you and you nod, I take that as acceptance that you've understood. And so in our system, humans kind of expect that same behavior from the robot point of view. So we have social actions like nodding thrown into the mix. Our main approach then from a planning point of view is to treat this problem as an instance of planning within complete information and sensing. And to do this, we are using a planner called PKS, which was joint work with Fahim Bacchus a number of years ago now. PKS is a knowledge level contingent planner that builds plans based on what the agent knows at any time. PKS is really, it's based on an extended strip style representation where the knowledge of the planner can be divided into 5 databases, each of which is restricted to modeling a particular type of knowledge. These databases then can be mapped into formulas in a modal logic of knowledge, which formally defines what the knowledge state of the robot or the agent is in this case. Actions in particular are defined in terms of the changes that they make to the planner's knowledge. In other words, the changes that they make to this collection of databases, rather than the changes they make necessarily to the world state. And then plans are generated simply by forward search, by searching through the space of the databases. And so actions update these databases, which has an effect of updating the planner's knowledge state, and we progress. So at the heart of this approach is really the representation of knowledge in PKS. And for those of you that aren't familiar with this method, there are 5 different databases we have for representing knowledge. The most basic one, KF, allows us to represent facts about the world. And so this is very much like a standard strip-style database, except we allow both positive and negative facts, and it's not a closed world assumption. KW and KV allow us to represent the effects of different types of sensing actions. So in KW, we can represent sensors that return one of 2 values. So we talk about knowing whether something holds. Whereas in KV, we can represent sensors that return more general terms. So things like knowing the value of some function. And then finally, we have a database called KX, which allows us to control a certain type of disjunctive information, in this case, an exclusive OR disjunction. And then a database called LCW, which is really based on ideas from Etzioni, Dan Weld, Keith Golden, a number of years ago now, that let us store local closed world information. And we don't really use that in this work, but it's available to us. So using this planner, we build up a domain for the bartender. And so we have a number of fairly high-level properties in our space. These are things like, is an agent seeking attention? Has he been greeted? Has he been ordered yet? Who are we in transaction with? And we have a set of pretty high-level actions, things like greeting a customer, asking for a drink order, acknowledging drink order, actually serving. Now, what's interesting is that many of our choices here about the domain were inspired by a data collection activity where we actually sent people into bars to understand what kind of actions they perform. And so there was this German master's student who actually did a thesis all about collecting data in bars. Somebody has to do the job. So if we take a look at some of the actions, so these are what actions look like in PKS, and they look very similar to strip-style actions, except you'll see some funny Ks in front of some of the preconditions. The K operator is just simply a reference to the knowledge state. So in this case, asking a drink, we need as a precondition that we know we're transacting with a particular agent. We don't know that agent has ordered. There are no other requests pending, and we've understood what the agent has said. The effects of actions are indexed by one of the particular databases. So it works like strips. We add and delete things, but to individual databases. So in this case, an effect of asking for a drink is we come to know that the agent has ordered, and we come to know the value of their request. In other words, what they've actually ordered. An important part of this process is state management. And we have a particular component which is taking the input modalities and trying to turn them into a high-level form that we can reason with to produce states of the form we're more accustomed to in the planning community. In our case, I mean, the state properties that end up being reported to the planner are things like the locations of agents, their torso orientation, whether or not they've ordered, did we understand what they said. And this is really coming from fairly low-level sensor information, things like raw vision, whether or not the robot arm succeeded in doing what they were doing. So given all this machinery, we can build plans. And so in this case, our goal is simply to transact, or in other words, serve drinks to all the agents in the bar that are trying to seek attention. So this is about the simplest possible plan that we can have in our space. And this is a single customer comes up and is attempting to order a drink. And so we can generate a 5-step plan where we greet the customer, we ask them for the drink, we acknowledge their drink order, and then we serve them the drink they're requested. So if you look closely at the fourth action in this plan, you'll see that there's actually a term there, request of A1, which is a type of runtime variable in some sense. It's a parameter which will get expanded at execution time to the actual drink that the person has ordered. But this is about the simplest plan that we can have in this space. And it really represents a best-case scenario. This is if everything goes according to plan, this is how you interact with a single person. We're also able to generate slightly more complex plans by branching. And this allows us, for instance, if we enter into sub-dialogues about certain types of drinks, someone orders a juice, we ask them what kind of juice you want, what kind of glass you want it in, do you want ice in the drink? We can use this type of branching structure. For two customers, we have a slightly more complex plan, which involves more of the social actions. So we have actions like telling one of the agents to wait, greeting the other customer, getting their drink order, then thanking the first customer for waiting, and then processing their drink order. And again, it's very similar to the single agent plan, but with some extra social actions thrown in. I just want to briefly say that we do an awful lot of plan execution monitoring in this space. When you interact with humans, humans are inherently noisy, they're inherently error-prone, things usually don't go according to plan. And so we're constantly taking a look at where our plans have told us we thought we'd be against where we actually are in the space. And sometimes we have to make changes. So two of the interesting places where things go wrong are, one, we've asked the agent something, for instance, for their drink order, and we didn't get a response back from them. So in this case, we enter into a replanning mechanism and possibly build a new fragment of the plan, something like saying, I'm sorry, I didn't understand what you said, and then asking for the drink again and continuing with the plan. A second interesting application of this is in over-answering. So sometimes we greet a customer and they give us more information than we expected. So they'll come back and say, oh, I'd like a beer. So in this case, we can actually detect that we have the information that we were going to acquire in the next action in the plan. We can actually skip that part of the plan, possibly through replanning, and continue. What's interesting is that in both of these cases, these are actually specialized methods that the natural language community will look at for solving these problems, and this just falls out of the replanning process for us. Okay, I have a very short video, if you can cue the video, to give you an idea of what the system looks like. So this is two people coming up to order a drink. One of them is not seeking attention.
Here is your drink. Thanks. Fine. You're welcome. Bye.
And I'll just show you a couple seconds of the second part here. These are now two people coming up, and they both want to order a drink.
Hello.
Hi.
I'll be with you in a minute. What do you want?
I would like a water, please.
Okay, you can stop the video now.
There you go.
And so then the interaction proceeds. Advanced slide, please. Okay, so I just want to just end by saying something very briefly about experimental results. In our case, if you go by the traditional planning metrics, our planning times are actually really quite short. So we're generating plans, say, with 3 agents, we're generating plans about 16 steps long in well under a second. And this doesn't impact the reaction time of the system. Usually anything less than 2 seconds is okay. So we actually have a lot of time to do a lot of planning. We've done a number of studies because what's actually more interesting is how humans perceive that we're doing on the problem. And so we've had people coming into the lab and actually ordering drinks and then surveying them and saying, well, how did you think the interaction went? And we have pretty good task success. We've got a couple papers on this that really delve into the numbers. And so I'm just going to leave that to you. So just to conclude, I guess the take-home message is really social interaction. When you're working in spaces like this, you need to think beyond just task. But we've done some interesting work, we think, on using ordinary general-purpose planning to solve what are problems that use alternative techniques in the natural language community for things like interaction management. We also think this is an area that has potential for exploring other types of planning problems. And so we're starting to look at things like planning with preferences and under uncertainty and constraints. And I'd like to refer you to the webpage. This is actually a EU-funded project. We thank our funders. We thank some of these other people listed here who actually helped build the system. And I thank you, and cheers.